Hi, I'm Jinyun Zhou. Thanks for coming to this presentation on our paper accepted by American Control Conference 2021. We're presenting a free space trajectory optimization algorithm called TDR-OBCA. Our work is inspired by a prior work called ThA06, which stands for Hierarchical Optimization-Based Collision Avoidance by Dr. Xiaojing Zhang. Our work proposed three different improvements to the ThA06 problem formulation, which includes trajectory temporal profile warm starting, dual variable warm starting, and objective reformulation. So the name TDR-OBCA actually stands for temporal and dual warm starts with reformulated optimization-based collision avoidance. The work is done and supported by Apollo autonomous driving open source platform, and the relevant algorithm implementation is already open sourced there. The collision avoidance is a critical factor to consider in nowadays autonomous driving applications. There are lots of scenarios which can be seen as unstructured free space, where the vehicle has to do some complex maneuvers going forward or backward to reach the destination without collision. It could involve cluttered road scenario, parking, and many others. For polygon-like ego vehicle and obstacles, the tricky part of collision avoidance in optimization-based ocean planning is how to balance between accuracy and computation complexity. There are different ways to do it. One is by mixed integer programming, solving which side of the obstacle polygon the vehicle has to avoid. It oftentimes involves solving with branch and bound technique, which is complex in real-time computation. Some others use circular or elliptical disks to approximate the shape of obstacles. It would not be accurate enough to cover the polygon with it, and sometimes the over approximation would waste some visible region for the vehicle to drive into. In TDR-OBCA, as well as in ThA06, we formulate the collision avoidance as a convex optimization problem of minimum distance between convex sets, as shown in the DAO in the graph on the left. The distance between the sets is a minimum distance between the points in each set. We use Lagrange duality to further transform the minimum distance formulation to a set of nonlinear constraints you could see on the right. With the collision avoidance constraint introduced, let's dive into the complete problem formulation. The vehicle states include Cartesian coordinates x, y, vehicle speed, and heading. The vehicle dynamics is approximated with the kinematic bicycle model. The collision avoidance constraint is incorporated with extra dual variables, lambda and mu. The optimization objective contains meaning two parts: trajectory smoothness and control efforts. Like in ThA06, we also apply hybrid A star to get an initial pass or path profile warm start. To further warm start the trajectory, we formulate a longitudinal speed optimization for temporal profile. The optimization is formulated as a quadratic programming problem with states of longitudinal position, velocity, and acceleration. The state dynamics is formulated as the third-order Taylor expansion of the temporal states. The objective includes minimization of acceleration and acceleration change rate. The dual variable used in obstacle collision avoidance constraints can also be warm started with quadratic constraint quadratic programming with the distance term minimized in the objective. In our work, we propose to move the quadratic constraint term into the objective function to form a relaxed version of the original problem as a simple quadratic program. It would lead to a suboptimal point, but it is much more efficient to solve. In the final nonlinear optimization, minimal distance d mean in the equation is a hyperparameter for minimum safety distance, but it is hard to tune for general scenarios. Besides that, both initial and end state constraints make the nonlinear optimization solver slow and in extreme case, hard to find a feasible solution. So to address the issues, the end states are relaxed to a soft constraint in the objective, and we add a collection of slack variable d into objective to relax the minimum distance keeping. We did simulations on parking scenario to test our warm start and reformulation techniques comparing with ThA06. The results show about 96% failure rate decrease, 3% to 44% increase in planner efficiency as obstacles number scales up, and 13% increase in driving comforts. Let's show a video including simulation and road test. First is a clip of reverse parking in simulation. The vehicle parks into the spots after it is clear. Then it is a road test. You can see the vehicle control tracks the trajectory closely. Then it's a zigzag parking, which means the vehicle has to do reverse gear in the process. Then it is a real-world test for the zigzag parking. You could also see the control module performs pretty well on tracking the vehicle heading, as well as the position. That will be all. Thanks for coming to our video presentation.